down to hard problems. And we've got a little bit of abstract computer science, abstract mathematics really tonight. So as usual, I'm going to have a pretty vague, hand-wavy explanation. I've been struggling for years. I have a little bit better explanation, but we're going to talk about the concept of what makes problems hard, and then some more things after that. But computational hardness, we've talked about some problems are hard, some problems are easy, and of course the whole point of cryptography is to find some problem that is hard and make it hard for your enemy to break into the cryptography. That's the idea. There has to be something hard. That's an intractable problem. And it would be nice if we really had a very strong mathematical, logical proof that the problem is hard, but we don't really have that. So you can measure the running time. For example, if you're searching through an array to find a number and this array is not sorted, then you just have to look at every item until you find it. So if you do find it, you'd expect to have to look through about half of them to find it. So if you don't find it, you have to look through all n of them. So this grows linearly with the length of the list. If you double the size of the list, it'll take you twice as long to find it on average. So that's one way to measure running time. And so you define complexity classes. You call that order n. So as the size of the list n increases, the time it takes will linearly grow. Now you can have, if you're sorting a list, then that takes more time. You have to go many, many passes through the list, and the best algorithms have n log n. Because what you do is you sort it into like categories, into like groups, and then you sort the subgroups. And that means you end up with n log n is how it scales. Brute force key recovery, what we've been doing, like AES, you have a key that's 128 bits, and there really are 2 to the 128 possible keys, and brute force, we just have to try them all, so that will grow as 2 to the n, where n is the length of the key. So this is an intractable problem. It's very easy to make the key long enough that this becomes impossible in practice. And there's quadratic time, n squared, that some problems are like that. So you can rate these things. Linear is considered easy, even quadratic is considered easy, but exponential is considered difficult. And this is just sort of a value judgment. You consider any power law to be what they call easy, because that grows as some power of the size, but things grow as like 2 to the n, those grow much faster. That's the idea. So polynomial time is these things, order n squared, order n cubed, order n. Those are considered easy. Super polynomial is anything that grows faster, like 2 to the n or n to the log n, and those we call hard. It's not, clearly it depends on the size of n, but in practice the point is raising n to a number you can achieve, you can make this impossible. And here you have more chance of keeping up by doing things like adding more processors and more memory and things like that. So, here's 2 to the n is this one, and this one here is n squared. And you can see they grow pretty fast, but as you move out a while, it gets much, much bigger. So 2 to the n really grows to an outrageous number. There's a famous ancient puzzle where someone promised to give someone some money. They said, I'll put 1 grain of rice on the first square of the chessboard and double. Yeah, it was ancient, and double the number on every chess piece. And even then, 2 to the 64 is an unthinkably huge number where you'd own like all the wealth in the world by the last square. That's the thing. And that's not true of n squared or n cubed. It doesn't grow that fast.
The version that I knew implied a grain of wheat.
Yeah. And you just
and 264 was,
and the point is, for the first 8 or so, you think doubling every time is not too bad, but after a while, doubling every time becomes impossible. Yeah. And that's all right. So so you can also have time complexity, which is mostly what we talk about, where it take more time. You could also talk about space complexity, the amount of memory it takes. Some problems are memory hard instead of time hard. Let's see. Counting sort is n plus k, not universally applicable. That's right. Okay, Dark Rogue knows more than some of these. All right. So now here's the stuff where it gets a little more abstract. So P is the class of all problems that can be solved in polynomial time. All right. And their NP, it would be nice if it was the problems that are not in P, but it isn't. It is something much harder to understand. It is the class of non-deterministic polynomial time algorithms. And these are problems for which a solution can be verified in polynomial time, but probably not found in polynomial time. And today, I found yet another explanation that seemed more clear to me. The technical definition of NP is problems that can be solved by a non-deterministic Turing machine. And a Turing machine is a theoretical computer Just processes things like any other computer with the tape and stuff, but that isn't what matters. What matters is here, we're going to have a normal computer. When you do a brute force algorithm, you guess the first bit, then there's two choices for the next bit. You have to try them one by one. Then there's two choices for each next bit here, so it doubles. It keeps on doubling with every iteration. A non-deterministic Turing machine can explore both branches at the same time. Now, no real hardware can do this. It would have to be like growing more processors. But that's the theory. And if you could do that, if you could explore both branches in a step of time, and then all these branches in a step of time, then it wouldn't take forever to crack a key. You just have to do 128 steps to do a 128-bit key. And you wouldn't worry about the fact that at the end you have 2 to the 128 processors. That's called a non-deterministic Turing machine. A Turing machine that can explore both branches of an if statement at the same time. So, of course, it's not possible to build this because 2 to the 128 processors is more than all the matter in the universe. So you can't really build that. But if you had one, it could solve this problem in polynomial time. In fact, it would be linear time. It would be linear in the length of the key. So that's an NP problem. It can be solved by a non-deterministic Turing machine in polynomial time. The only problem is we don't have one of those. However, if you know the key, then you know which branch to take at every step, and then again, it's only a problem in linear time to verify the key. So that's why the description I've heard, which is more realistic, is this one. These are algorithms where you can verify solution in polynomial time, but you can't find it in polynomial time. Anyway, this, I think, helps me understand why they call it NP. This is the name. It can be solved in polynomial time by this non-deterministic Turing machine, which doesn't exist.
I'm not sure if the author is not using the appropriate language, because rather than verify is really testing. You are testing that the solution that the potential solution you have attended.
That's right.
You try, test, failed, okay.
That's right. But the test only takes polynomial time. Right. So if you had the right key, you could prove it in polynomial time. Right. That's the idea. But which is the point, of course. If you have the key, you can read the stuff. If you don't have the key, you can't. So it achieves the goal of cryptography, right? Yeah. But all right, so anyway, that's NP. And so here's the problem. There are many examples of NP problems, and the one, of course, obvious to us, is that if you know the plain text and you're trying to recover the secret key, it's easy to verify whether the key is correct, but finding it is hard. Or at least we think it's hard. And of course, like I say, it would be nice if we really could prove with certainty that it's hard, but we don't have that. All right, quantum computers do that, but not all. Yeah, what quantum computers do, quantum computers don't exactly do this. What quantum computers do is they don't work on bits, they work on qubits, which have much more information, and they have strange interactions between the qubits, like entanglement, that are not much like NOT and XOR, like you get with normal bits. So certain operations become faster on quantum computers.
Superposition, I think.
Yes, you have this superposition, and you connect these positions. Each qubit has much more information than a bit, and the interactions between them are strange. So certain operations are fast. So quantum computers cannot solve this problem the way a general Turing machine, not equal to this, because a quantum computer cannot crack AES in polynomial time. All it can do is it can do it in a square root of the number of steps. So it could crack a 128-bit key in 2 to the 64 steps. So AES 128 is in principle in danger with quantum computers, but AES 256 is not. All you have to do is double the size of the key, and quantum computers become useless. Now, for public key encryption, though, they destroy all current public key systems, RSA and elliptic curve and all of them, because it can solve essentially, it can solve the discrete logarithm problem we'll talk about, which is the underlying problem for all of them. It can solve that problem much faster, not just the square root of the number of steps, but in principle so fast that no length of key would ever work. Even a key 1,000,000 bits long would not be enough. That's why we're moving to new algorithms for public key encryption. But for private key encryption, there's no need to move to a new algorithm. The worst we'd have to do is just use the stronger version of AES with a longer key. Yeah, good. Yeah, good. Okay, well, I see dark. Anyways, that's the game. Yeah, but that's right. A quantum computer is not a non-deterministic Turing machine. That would be awesome. It does have some advantages, but it doesn't do this. So far, nobody has any proposal for any actual hardware that could do this. It would seem to be impossible to build any hardware that could really do that. But as a mind experiment, it helps understand the concept. So those are the NP problems. Now, here's one that's outside NP. If you brute force the one-time pad, remember the one-time pad, you have a series of random letters. Each letter is encrypted with a different key letter, and the key letters are random. So if you try all possible keys, you will generate all possible series of letters. And a whole bunch of them will be readable messages. You'll get all possible readable messages with that many letters, so you don't know which one is the message. Even if you do a brute force attack trying every possible key, you still can't solve the problem because you don't know which one of those messages is right. Now, normal encryption algorithms like AES have the property that if the key is wrong, you get random garbage. It will only turn into readable text if the key is right. But that is not true of the one-time pad. The one-time pad will create many readable messages, all possible readable messages, so there's no way to tell which one is right. So this is outside NP. You can't solve it even with a non-deterministic Turing machine. You can't solve it at all. It's just plain impossible as far as anybody can understand if you don't have the key. So that's interesting. That's why it's not true that every problem is in either NP or P. There are problems that just can't be solved at all. All right. So there's a group of NP problems that are called NP complete problems. And they are the hardest problems in the class NP. And they're all equally hard, it turns out. If anybody ever finds a way to solve one of these, they can solve all of them. They're all fundamentally identical. And those are the famous ones you've heard of, like the traveling salesman problem. If you have a list of n cities on a map, what is the best route to visit those cities with the minimum total distance? If you have a graph and a series of nodes, determine if there's a set of points so all the points are connected to each other. So you have a graph like this, and you want to say, is there a node that has like 5 nearest neighbors? This one has 4, this one has 2, that sort of thing. Hunting through a graph for that. And another one is the knapsack problem. If you have a bunch of objects, and you're trying, like they have a dollar value and a weight, and you can only have a certain maximum weight, what is the maximum dollar value you can pack in the knapsack of objects? All of these turn out to be pretty much the same. And all of them are considered NP complete, the most difficult problems in NP. And none of these are easy to solve on computers. Rapidly they become out of hand trying to do all combinations, and there are various ways to approximate an answer.
I mean, with the caveat, it seems that the author specifies, because yes, in general, NP complete problems are the hardest. But there are some instances that instead are easy, and the upper part of the graph is.
Yeah, that's right. Yeah, there are certain cases in which they get easy, and there are, and of course, with small numbers you can do it. Yeah. All right. So some video games are apparently NP complete, like Super Mario Brothers. I don't quite know how to prove that. By the way, notice there's also something even harder called NP hard, which is so hard maybe it's not an NP. So this is where I can't really explain this in detail. This is the abstract mathematics as set theory. Somehow they figure this stuff out. Anyway, in practical terms, here's the issue of P versus NP. So people would like to know, this shows you how fundamentally cryptography is a mess. If NP is equal to P, then every problem has a fast solution, and we just haven't found it yet. And that is possible. There's a $1 million prize out there for decades for anybody that can prove whether P equals NP. Nobody can prove that. All we know is there are problems where we haven't found a fast solution yet. But factoring was the famous one. For breaking a number into its prime factors was considered the hard problem for 2,000 years, and now we have quantum computing that can do that problem. So we can't really do it yet, but we do have significant evidence that probably in a few decades we're going to have machines that can do it. So there are problems that we thought were hard that turned out not to be hard. That happens. And if your cryptography is based on one of them, then sometime in the future they'll be able to read your encrypted messages without the key. That's what we're worried about. So that's why the whole thing is founded on sort of a best estimate guess, not on what you'd hope, like perfect mathematics proving that what we're doing is safe. So does P equal NP? Now, most people say no. Of course, if P equaled NP, then there would be no hard mathematical problem at all. All the ones would have an easy solution, and it seems like there are hard mathematical problems. I've taken mathematics like you guys have, and there were problems that seemed pretty hard. So it seems like there are hard problems. But, We'll see. So far, nobody's proven it. And of course, quantum computers change it. So now they're developing BQP is the new theory. All problems that quantum computers can efficiently solve. People are trying to extend this logic of P, NP, and so on, and try to figure out how quantum computers change it. Because a quantum computer is not really a Turing machine anymore. Turing machines use bits. And so quantum computers don't actually do bits and bit transformations. So I guess technically, it's outside, and they're trying to figure out what is this group of things you can solve in a quantum computer, and how does it relate to these? And this is currently, people trying to figure this out. So, all right. And so anyway, there's a XKCD about it. Like, here's an example. If you have a restaurant that sells you food at various prices, then he can just say, I want the total price, and you have to figure out which items will add up to this total price, and that's the knapsack problem. It's not simple. It can be far more difficult than you think, even with a relatively small list like that. And all right, so breaking a cipher where NP complete, that would be a strong cipher. But the problem is NP complete problems turn out not to be good to use because, as you mentioned, there are certain cases where they're easy. Like if you solve the graph problem and the numbers are just in a line, then the graph problem gets easy. So it's not always hard. The fact is that the general problem is hard, but certain cases are easy. The same thing's true of RSA, by the way. If you don't choose P and Q carefully, there are certain prime numbers that make it easy to crack. So it's a problem. So real cryptography uses problems that are probably not NP hard, but they choose problems where they can feel like they're high confidence that it's difficult to solve. So anyway, lattice problems is learning with errors. These are two mathematically equivalent operations where you're finding the combination of vectors that will connect 2 points on a lattice, or learning with errors, where you have some data you've measured, but there are errors in it, and you have to deduce the trend on anyway. This is what Kyber uses, which is the new approved post-quantum cryptography standard. So it's what we're using. That's the lattice problem. All right, so anyway, the factoring problem is the one we use for RSA. So if you have a large number n that's the product with two primes, find the primes. How difficult is this problem? Well, it's quite difficult. The obvious way to do it is to just try all the numbers less than n, try to divide and see if you can find it. So you can try them all. If you think a little bit more, you say, well, I only need to try numbers up to the square root because one of these numbers, p, must be below the square root and the other one must be above the square root. So I don't need to try anything past the square root. If I go up to the square root, I'll find p. And there are a few ways to get even faster. But if you did that, that would scale as linear with n. And so if you count the number of bits, it would scale as 2 to the n, where n is the number of bits. And that would be a hard problem. But there are faster ways. The simplest algorithm, try all the numbers from 2 to n minus 1. That's a hard problem, 2 to the n. For 256-bit n, it would take 2 to the 256 operations, which is unthinkable and impossible. If you improve it and only try to go to the square root of n, then it will be 2 to the n over 2, over n apparently. But anyway, this is that's still hard, but much easier. But it would take 2 to the 120 operations to crack a 256-bit public key. Still impossible, but getting better. Now, in practice, there are faster algorithms. The original one was the sieve of Rasines. You take a prime number like 2, make the number line. You take a prime number like 2, now you cross out every other number because they're all divisible by 2. Then you take 3 and cross out every third one. Then you take 5 and cross out every fifth one. And so more and more of the numbers are excluded. And this process, you find the prime numbers. But anyway, there's a thing called the general numbers field sieve that works like this, and this can do a 1024-bit n in only 2 to the 70 operations. And this is why our keys have gotten bigger. 2048-bit that we were using for a while requires 2 to the 90 operations. And as you know, 2 to the 90 is not really as much as you want, because I think we tried a couple lectures ago, I took the Bitcoin, the best measure of computing in the world, and I think they were doing something like 2 to the 82 calculations per year on the whole Bitcoin blockchain. So 2 to the 90 is not completely unbelievable that somebody could do that many operations. So now they recommend 3072 or 4096 bits. 4096-bit keys would give you 128 bits of security. It would take something like 2 to the 128 operations to crack it, and that's pretty good. But of course, quantum computers will blow this all out of the water. So that's the game. And here's the experimental results. In 2005, they cracked a 63-bit n. And in 2009, they cracked a 768-bit N. People speculate that the NSA can factor a 1024-bit N because they have secret computers. So, this is the issue. That's why I told us you probably have to quit using 1024 bits. You should be using 2048. Within a few years, you should be using 3072. And that's the current state of the art. So is factoring NP complete? No polynomial time algorithm is known, but you can vary it. So it appears to be, it's in NP. It's probably easier than NP complete, but nobody's proven this. And so quantum computers, and like I say, quantum computers can factor numbers easily using quantum algorithms, but the hardware doesn't exist that can do it for a major key. The only thing I ever heard that was successfully cracked was this. They proved, they factored like 15 into 3 times 5. This one's doing a different one. But in real quantum computers, they proved that 15 is 3 times 5. That's the factor they were able to do.
In quantum?
Yeah. So, they're nowhere near cracking a real RSA key. They've proven it works, but the current qubits are so noisy that you can't put in a really big number and crack it. They have to get like 1,000,000 times better than they are before they're a real risk. So you start from a problem that's assumed to be hard, and then you can sometimes prove that it's as hard as another problem. So these are common problems. Factoring discrete logarithm problems are pretty well understood problems, and you often compare new algorithms to these. So this is what you do. You can't prove that they're secure, but you can prove they're at least as strong as something else that you think is secure. That's what our math is based, our cryptography is based on, a whole lot less reassuring than you might wish for. So, a group. You have a set of elements and an operation. This is the idea. This is a generalization of things like RSA. RSA is more general. This is the more general mathematical structure underlying our all public key encryption. You define a group. Now, a group is a set of elements and an operation, and this ZP star is the numbers from 1 to P minus 1. So Z star 5 is the set 1, 2, 3, and 4, an easy group to understand. But, okay, so here's the group axioms. In order for a set of objects and a operation to combine them, to be a group, it has to have these 4 properties: closure, associativity, identity, and inverse. And so closure means for any 2 elements in the group, if you combine them, you're still in the group. So your operation, the group is closed. You combine elements and you stay in the group. Associativity means you can do them in a different order. You can do X times Y and then times Z, or you can do X times Y times Z. That's another property. If you don't have that, then you haven't got what's called a group. You've got some other kind of structure. Identity means there is an identity element where identity times every element gives you the element back, like 1 for multiplication. And there's an inverse. For any X in the group, there exists an inverse. And we did this a while back. We were doing like modular inverses. And sometimes it's something you can multiply by, it gives you 1. Now, there are some things that don't have an inverse, like 3 mod 9 has no inverse, because no matter what you multiply it by, you always get 3, 6, or 9. So there are objects that don't have an inverse. But anyway, for any X in the group, there exists a Y, so you get the identity element by multiplying together. So, all right, that's the idea. And that's commutative groups are where for everything X and Y you can multiply in either order and you get the same answer. That's the general structure. And as you can easily see, RSA follows all these rules, but there are other mathematical structures that also have this formal structure. So that's the idea. And there's cyclic groups where there is a generator, and all you have to do is raise it to powers, and you can generate everything in the group by just raising it to many powers. All right, so now you can define the hard thing. Since you have a cyclic group, so for every element in the group, I can take the generator to some power and create that element of the group. I can now define a logarithm. A logarithm means if I have X, and I want to know what power would I have to rise the generator to get X, that's the logarithm, finding the Y. So that's the discrete logarithm problem. And if you think about it, this is essentially the hard problem in RSA, and all public key encryption is based on this hard problem in this sort of abstract mathematic sense. So within a group, Z star P, where P is a prime number and X is a known group element, this problem is about as hard as factoring prime numbers into the composite number into their primes.
That Z sub P star is the module, right?
This is the group,
can be the
which is 1 to p minus 1. This is the group of integers from 1 to p minus 1.
It's the group of
Yeah,
integers.
yeah. Where p is a prime. This is one possible example of a group. You take the numbers from 1 to p minus 1, where p is a prime number. That's a group. Yeah. All right. So anyway, that's the general. I mentioned this stuff, which if you don't understand it, don't worry about it too much. Just the abstract mathematics. It's nice if you like that stuff, but for practical purposes, you don't really have to understand it in any detail. But this underlies the other algorithms we're going to talk about that are not RSA. There's a discrete logarithm technique, and there's elliptic curves. They all fall in this category. And they all look like RSA, really. They're just the symbols mean slightly different things. If you understand RSA, all public key encryption is a lot like RSA, just it uses a different operation than multiplying and exponentiating prime numbers. It uses a different transformation, but it has this same structure. Anyway, so let's take a look at how things can go wrong. Here's things that might go wrong. For example, if p equals np, well, that would ruin everything. Now, nobody thinks that's going to happen, but of course, that's something that could happen. When factoring gets easy, there are also, like I mentioned, there are sometimes it's easy. This 1024-bit number is easily factored because it's multiple prime numbers, and one of them is small. So if you just start dividing by numbers, by the time you get up to here, you'll be able to divide by something. Then it will get smaller. Now it'll be easier to find the next one. So, if one of the prime numbers is small, then it would be easy to crack. And as we've seen in the projects I showed you last week, if 2 prime numbers are close to each other, then it's easy to crack. And there are other ways it can go wrong too. If they're near a known value like 2 to the b, or if some bits are known, or if n is small, and there are other cases. There are quite a few cases where RSA fails. There are prime numbers where it gets to be easy. Like you mentioned about the NP complete problems, the problem with sometimes they're easy. And you really need something that's always hard. OpenSSL will let you generate short keys. You can make 31-bit keys if you want to. Well, that's of course useless. I mean, anything less than like 1024 is pointless. But anyway, you can have small RSA keys, just they're not secure. And people, the original RSA paper, back at this time, they figured that it was going to take forever for like 200 digits. They recommended 200 digits long, which is a 512-bit key. The original paper, which was from 1978, said a 512-bit key will be secure, and it probably was in 1978, but computers got a lot faster, so it's not secure anymore. All right, and that's we're all used to. Every encryption scheme, after a few years, you have to move to another one as it gets cracked. Then there were some attacks. The logjam attack is one. This is a political problem because the United States decided that cryptography was too dangerous to export. They forced Microsoft and other companies to make crippled versions of their operating system. Microsoft called it Windows N, which would use weak encryption to export to countries we didn't like Russia and China. So now the internet is full of machines running these N versions of Windows that can only use weak encryption. So if you put up a website and you want people in China and Russia to see it, you have to allow weak encryption. And therefore, if I have a man-in-the-middle attack, if I can intercept your traffic, I can change your traffic as you request a web page to say, oh, I'm using an N version. Send me the badly encrypted version. This is why the cryptographers hated this. You've now polluted the internet with a bunch of machines that can't use good encryption. So now, this means pretty much all the servers have to deliver broken encryption under certain conditions, and that's a dangerous thing. So that's what the logjam attack did. Yeah.
Isn't there a double encryption? The encryption that the computer does and the encryption that happens on the network because of the protocols, no?
No, just on the computer. The network just delivers packets. It doesn't encrypt them. In fact, it can't encrypt them because it needs to read the addresses in the clear. Yeah, the data is encrypted, but the network never sees that.
So everything happens in the machine, then the encryption happens on the machine,
Yep.
and then it's deleted.
Yeah, the surfer does encryption and your browser does encryption at the two
server.
ends. In the middle, there's no more encryption unless you're using like the Tor network. The Tor network adds extra encryption. And if you use a VPN, that adds extra encryption, but it's still actually done on your machine. Yeah, yeah. Yeah, this is good. All right, and of course, there's another issue that there's a particular secret prime number used by many machines, and it appears the NSA has done so. So if you use certain recommended numbers, it's probably true that there's a backdoor. So these are issues, various things that can go wrong. And here's the ones vulnerable to logjam and vulnerable if the most common group is broken. There's issues of how many websites are vulnerable to these, and a lot of them were, at least a few years ago when this research was done. So, you know, this is the problem. A lot of people are not using good encryption. By the way, I just saw a paper today. Cloudflare checked the logins, and they found that 40% of all logins are using known compromised passwords. People are reusing bad passwords, which is not too surprising. So as you know, even though we have powerful encryption techniques, a lot of people incorrectly use it. So it's not safe, and that's why I said it's what motivated me to teach this class. I started looking at Android apps, and more than half of the Android apps implement encryption wrong. And I said, this is awful. We have systems that work, and people just don't use them correctly. So it would be good to actually teach people how to use your encryption properly. So let's take a look at a Kahoot. You know, if you do correctly employ things like RSA and AES, they're really very good. I mean, nothing is perfect, but you can really protect your data pretty well with these standard algorithms if you employ them correctly. So chapter 9, there it is. All right. Oh, by the way, I'm dressed like this because it's cold here. They turned off the heat for some ungodly reason. You guys are lucky you're at home, most of you. Anyway, the two of us that are here are having to tough it out. Anyway.
Actually, this is the first time I see it.
Yeah. I'm thinking next time I'm going to bring more socks. Anyway. Yeah, yeah. Yeah, moving around is another good move, yeah. Well, we may only have 2 competitors today. There's only 8 people in the room. I think this is probably it. Such is life. The few, the proud. we charge ahead regardless.
We fight for the first place then.
Yeah, yeah. Right. All right, so which is the hardest complexity class? Yeah, exponential. 2 to the n, that's the biggest among these. All right. All right, where's the easiest ones? P are the easy ones, the ones where you can solve them in polynomial time. All right. All right, which one is the knapsack problem? Yeah, NP complete, not NP hard. NP complete are the hardest problems in NP. The NP hard ones are even harder, and they think maybe they're not even in NP. So these are the hardest ones in NP, the knapsack problem, the traveling salesman problem, and so on. All right, how about factoring? Well, it's in NP. It's not NP complete. It's not as hard as the knapsack problem, but it is in NP. That's factoring. All right. Yeah. All right. And yeah, well, you know, this is abstract theory, really. But anyway, how long should your RSA key be to give you enough security? Now, there's a practical. That's practical answer if it matters. Yeah, 4096 is what you need. 1024 has not been any good for a long time. Most people are currently using 2048, but they got to move up. We're hitting about the end of trusting 24.8. 4096 is what's recommended now. All right. Or 3,000 something in between, you know. So. All right. So we stop this recording.